Hello everyone. Uh, this is a series of lectures on quantum field theory, first course to quantum field theory. So here we will learn the basic techniques of quantum field theory. But before that, what we will try to do is we should try to understand why one should learn quantum field theory. Okay, so whenever we say QFT, it's a short form for quantum field theory, why one should learn quantum field theory. So this is the first thing we would like to understand. In order to do that, let's first start from a review of very basic things about quantum mechanics. So the formalism of quantum mechanics says that every system, every quantum mechanical system or every quantum particle corresponds, this is corresponds to mathematically or to a Hilbert space. Okay, so a state of a system corresponds to a ray in the Hilbert space. I did not write a vector, I said it's a ray because we will use Dirac bracket notation. So let's say if there is a state psi, and if we just multiply it by a complex number lambda, they correspond to same state. Okay, so that's why every state corresponds to a ray in the Hilbert space, and then physical observable corresponds to Hermitian operators. So more generally we will consider other operators which are not necessarily Hermitian, but you should always remember that the physical observable corresponds to Hermitian operators. Okay, so this is a very basic way to think about a quantum mechanical system. So I denote it as Hilbert space. Now, if we want to learn quantum field theory, so then the first thing you probably remember is that quantum mechanics is a quantum mechanical system is obtained after quantizing a classical mechanical system. Okay, so then at this point a very natural question which also leads to quantum field theory, which is just a question about the formalism, is that what about quantizing classical fields. Okay, so this is a question on the formalism. Okay, but the perspective, so this is one good reason to, so this one, and the answer to this question leads to quantum field theory. But actually there are, it's not just the question of formalism, but there are also other motivations to learn quantum field theory. Okay, so it's not just a question of just if it's just a question of formalism or just a natural extension of how to quantize classical fields, one may say that okay, I am a very practical person, I don't care about quantizing a classical field. What if just I am happy with quantizing classical mechanical system? Then why I should learn quantum field theory? Okay, that's a very valid question, and the answer to those questions is that, and that's the thing we will try to understand, is Q of t is a natural, we will explain, framework to explain many body physics. Okay, so in order to understand that, we have to understand firstly, so to this has a wide application in condensed matter physics. High energy physics, and many other disciplines. So let's try to understand this point. So in order to understand this point, we start from the phrase many body physics. This essentially means that if it's basically, it's a collection of multiple quantum systems. Each system, the Hilbert space of this, all this, the Hilbert space of each such system is same. Okay, so for example, one example could be like, let's say, collection of electrons. Or say okay, so here there will be a very important aspect which we will discuss later. It's the aspect of identical and indistinguishable particles. We'll come to one future lecture, but for at this point, we just try to understand that what happens. Let's say, forgetting about this feature, that whether this feature has to do with whether we can distinguish two such quantum systems. Okay, we'll come to that. We'll come back to this. For this moment, assume that we can distinguish it. Okay. So in that case, let's try to construct the multi-particle Hilbert space. So if the single particle Hilbert space is H1, I mean the 1 is the level of the particle, so single particle Hilbert space is H. Then the multi-particle Hilbert space is simply tensor product of n copies of the single particle Hilbert space. Okay, so what I wanted to say is that the n particle Hilbert space. So okay, let's use this notation that the superscript says the number of particles. And subscript says the I mean, it basically says it's an index for the particle. Okay, so for example, if I write this, then this means it's the ith particle, and this is the single particle Hilbert space. Okay, so with this notation, the Hilbert space for n such particles is simply the tensor product of one particle Hilbert spaces. Okay, this is the tensor product. Very good. Now what about the operators? Okay, so so in order to do that, so let's say there is a single particle operator. Okay, so I should have mentioned that this statement, this way of constructing multi-particle Hilbert space, is true only if there is no interaction. Okay, so in presence of interaction, we have to review this statement. Okay, you should keep this in mind. And in fact, this is not always true. And one such example is that bound states. Bound states cannot be obtained in this way. Okay, so this construction of taking tensor product of states, this is not necessarily true in general. This is only true if there is no interaction. Very good. So now let's talk about single particle operator. So let's say there is an operator F. Okay, so F. So let's say there is a state I. So there is a simple action like, so this is a state of single particle Hilbert space. Actually, let me change the notation. So there is, I use I here, and for particle index I use R and S. Okay, so this is the state of this. Then Fi is this is the action of the single particle operator on the single particle Hilbert space. Okay. So the statement is that the operators for the collection of this free systems, in that case the multi-particle operator F. Okay, so I use it in the note as mathcal F in the note. So this is simply collection of all single particle operators. Okay, so for example, if we construct the Hamiltonian, then the Hamiltonian of the full system simply collection of the Hamiltonian of individual systems. See the single particle Hamiltonian. Okay, and again, as you know, that this statement is only true for free systems also. So let's now try to see that how these operators act on the multi-particle Hilbert spaces. So let's say this F tilde, this will act on the n particle Hilbert space, which is simply the product of one particle Hilbert spaces. So now in order to do that, in order to find this action, so let's just try to find the action of f of r. So the way f of r will act is that action of f of r on Hn, it is simply something like H1 H1r on the rth Hilbert space of rth particle. This acts on this way, and on any other Hilbert space it doesn't do anything, it's just identity on the Hilbert space of other particles. Okay, so to be more precise, f of r when acts on this, on the n f of r on n particle Hilbert space, you can think in this way, it is simply identity times dot 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 in case of rth. So this is 1 dot 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 rth place, and then this is just identity. Okay, so this is a way we can just construct the action of f of r on multi-particle Hilbert spaces and then once we know the action of f of r, we know action of f. Okay, so this is the a very basic introduction to multi-particle Hilbert spaces. So let's say that to summarize, we assumed, considered collection of multiple quantum systems we assume they are distinguishable. We will very soon change this assumption that this is not a correct assumption, but for the moment we assume that the distinguishable. And also assume there is no mutual interaction. In such context, we constructed the Hilbert space. And operators on Hilbert space. And operators on constructed the multi-particle Hilbert space. Okay, so with this input we will end this part of the video, and in next lecture we will see that what happens to this assumption. And if it is not true for quantum systems, then what are the consequences? Okay, so with this we end this session of video, and we will see you in the next lecture.